Okay, welcome back. Again, I apologize if I sound lispy. I have my retainers in. But what are we gonna do now is continue with the test set creation process. So basically, I already did this. I'll just do a quick recap of it, a quick review of it. So basically, this is the way, the first iteration of how we create a test set. It's theoretically very simple. We pick some instances randomly, typically 20% of the dataset or less if our dataset is very large, and we set them aside. So basically, this is the function that we have. This is how you use this function. Name housing is not defined. It's not defined because I need to run all of these cells above. And now if I run this and if I run this, okay, it works. So in the last episode, I said that this is not exactly a perfect solution because if we try to run this again, we will get a new test set. And if we generate new and new test set, we will actually go through the whole dataset, which we don't want to do, basically. So we need a way to have and to generate every time concrete test sets that are unchangeable. To ensure that this notebook's output remain the same every time we run it, we need to run a random test set. Okay, how can I close you? Okay. Sadly, this won't guarantee that this notebook will output exactly the same results as in the books. There are other possible sources of variation. The most important is the fact that algorithms get tweaked over time and libraries evolve. All right. What we basically need is a stable train/test split even after updating the dataset. So how can we do this? And here is a possible implementation that we also showed in the last episode. So we have this code here, and the purpose of it is to split a dataset into a training and test set, as we said, but to use a deterministic way, using a hash of the ID. So the same data will always go to the same set, even after, I don't know, updating or shuffling. As we said, this is really good because we don't want data leakage. We want repeatability when training models. So what do we have here? We have the first method that takes an identifier, and we will provide an identifier to this method when we use it. But the identifier is basically a row index or a unique ID, and we will hash this identifier using CRC32, which is a hashing function. And we will return true if the hash is less than the test ratio, but then the test ratio times 2/32, which means if test ratio is 0.2, it returns true for 20% of the IDs. We also have a split data with ID hash where we provide the data at the test ratio and the ID column. And we get the list of all IDs. And then we apply this method to each ID. And basically we will use the result to split this data into two splits. In test set, which is not in test set, lambda in test set, and in test set, which is in test set, which goes to test set. And that's it basically. Now if I print this out, we have our train set and we have the head of the train set. Now let's talk about some other very important concepts here. What we did here is actually we picked and we selected our training and test sets using completely random sampling, which means we selected rows at random. This is okay. This is okay if the data set is large, if the data set is well balanced. But when the data set is small, or we have a feature that is maybe important, we might accidentally put too many data points in the test set, or add too few data sets in the training set. Basically, if we have a feature we can add on either side of the data, we might add too many extremes. So what we need to do here is to group the data into income categories, a kind of bucketing, so to say, which is we do this to make stratified sampling possible. Now, what is stratified sampling? Stratified sampling ensures that each group or category in the dataset is represented proportional both the training and test set. So it's useful because if 20% of our data has low income, stratified sampling will ensure both training and test set also contain 20% low income rows. And in practice, how we will do this is that we will create, let me maybe share my screen. So, okay, so basically, we ensure that each group or category is equally represented. And how it works is by creating a new column that divides income into categories. And then we use a split or a similar tool to split the data while preserving category proportion. Splits into categories. Use a split helper. So let us try to understand the split method. So the split method is found in scikit-learn model selection. And that's where we're going to find stratified shuffle split, which is a method that takes certain data as its arguments. It takes the number of splits, and we will generate here the number of train/test splits depending on the number that we put here. We can also put test size, which is another property which says, okay, 20% of the data goes into the test set. And we can also have random state, which just ensures reproducibility, basically saying, okay, we are gonna get the same shuffling every time. And what we can do, let me just close this. So how we can do this is, let me just see here. Okay, so before we get to train and test splits, I think it's okay, it's down there. Let us just go over some code snippets. So this specific code snippet is creating a custom deterministic identifier for each row. And this identifier will be used later to split the data into training and test sets, even after shuffling or modifying the data set. So what do we have here? We have our housing, basically saying, okay, each row in the data set represents a house. So each row in the data set represents a house with a longitude and latitude. If I print this now, print housing with ID, and if I run this, ID, where is the ID? Okay, it's here. But why doesn't it have a name? Where are you? Where are you? Open text editor. Can I see all of these? No. Index, longitude, latitude, housing median age, total. Ah, here's the ID. Why haven't I noticed it here? All right, I didn't have the full view. So here's the ID. Basically, the result that we got is a numeric ID that reflects the house position, and somewhat it should be unique, hopefully. Pardon me. It just ensures that houses in similar locations have similar IDs. And then we split data with ID hash from this set, from this data frame. Again, we take 20%, blah, blah, blah. We split it on the ID. Okay, it's useful. It's useful because it's, again, stable splitting. There is no randomness. It's great for data sets which are versioned. Also, we might use it for geographic consistency, where houses near each other might share some similarities when it comes to testing and training. Let's say, I'm just guessing, I have no idea. But that's not what we want. That's not what we want. That's not what we want. We also have this. I think these are just examples. These are just examples. Okay, so yeah, this now snippet of code that I'm gonna select is using random sampling to split our housing data frame into a training and test set. Again, these are just examples. I don't think this is needed for now, but let's say for housing, maybe open my tablet again. Let's say if our housing data set had 10 rows. So what do I have? 0, 1, 2, 3, 4, all the way to 10. The income can be, I don't know, 4.5, 3.2, 2.8, 6.1, 5.0, I don't know, another property here. So we have 10 elements. I just didn't add all of them. So with test set 0.2, what we would get, in the train set, we will get 8 rows which are randomly selected. And in test set, we would get 2 rows which are also randomly selected. But if we have this, if you use the same data, just imagine that they are 5, 6, 7, 8, 10, and 8. Well, so because of random state, we will get the same rows in every split. Now, the next line, which says, okay, test set total bedroom is null, sum, this checks in the test set data frame. And it looks, okay, I need to close this. Yes, this is the code that I wanted to. So it checks the test set data frame and looks at the column total bedrooms and it finds where the value is none. And it counts how many missing values are there, which is okay. Okay, I don't need this. I don't need this. But from here now, okay, here is the part when things get interesting. Here is the good part, the meat. Okay, let's go over the first snippet. Basically, what we have here is a code snippet that will take our housing data frame. It will take the median income category variable, and it will create bins of categories by binning the values into defined ranges. So, okay, PD cut just splits a numerical column into intervals. It's just a method name. This is a variable on which we split, and these are the bins, or the edges of the bins that we create, from 0 to 1.5, 1.5 to 3, 3 to 4.5, 5.5 to 6, and 6 goes to infinity, and we have a label for each bin. Okay, and here, what if I run this? What if I run this? Okay. And here we are actually looking at this new variable that we create, this new category that we create. We count values, we sort them, and then we plot them here. So we can actually see how many income categories we have. A pretty small amount of low income categories. We have the most amount of middle income categories, and there is a smaller amount of high income categories. But this is it basically. Now, here we have the stratified split code logic. So what we did beforehand is that we created these bits. Now, this piece of code here will perform stratified samplings. Here it says 10 times. We'll most certainly use only the first split, but yeah, let's go over the code. So we imported the stratified shuffle split, provides train test indices to split data in train test sets. This will split data, this method, while preserving the proportions of values in income category. So here it goes. We have the number of splits, which is 10. Again, test size 0.2. I don't need this. Random stakes 42. So now we have a splitter. And now we split on this splitter, basically saying, okay, this whole stratification is based on the income category column. And if I do here print housing income category. Okay, now we can see all the categories that we have. And each iteration of this loop right here will get the row indices for train and test sets. It will use iloc to select these rows. Iloc is a method that is purely integer location based indexing for selection by position. Basically, we are just selecting it by position here because we are doing this on a data frame. We are not doing this on a real array. Okay, so this is the train test set. Okay, housing iloc, is this a train index or not? Then we have the test set, and then we append these in our train and test sets. Okay, I was just looking and I was interested in why the train index, why printing the train index returns a whole array. I know that the split method gives us back two properties on each iteration. Train index, which is a numpy array of row indices, and test index, which is a numpy array of row indices for the test set, and this is a numpy array of row indices for the training set. These are just the positions. They are not data of the rows selected for each split. And if I had 5 rows in housing, I might see something like this, which I already did. We might see something like train that could be 0, 2, and 4, and the test set could be 1 and 3. And what we actually do, we use iloc to get actual rows from our data frame, which will give us proper pandas data frame for each split. Okay. So just a reminder. And I think, yeah, we have only this code snippet before we go to the next section. I don't even know if this snippet is important, but let's just quickly go over it. This piece of code compares how accurate our training test splits are in preserving the original proportion of income category values. So basically, what this method does is it calculates the proportion of each income category value in a data set. So we have our data, we get our income category, how many values we have, divided by the length of data. Basically, we we want to check how many rows fall into each income category. Okay, we create a random split here. We compare proportions here, and I think we just create a table. Check the table, and we can see our error percentage columns. All right, so we are discovering and visualizing the data to gain insights. The first snippet of code here in the chapter deals with copying the training set. So why are we making a working copy of the train set here? So we are doing basically so we can experiment on the new set, but we will still have the original stratified training data untouched in case we want to create a new process, try a different transformation, or compare the original versus modified versions. It basically just a working duplicate. I don't think we should think, oh, I need to run all of these above. I don't think we should think too deeply into this. We are just creating a working copy, a working duplicate of a clean document, so we can work on it without damaging the original. Okay, now this chapter is called Visualizing Geographical Data. And what this does is that it creates a scatter plot of California housing districts, and basically by the shape we can see the outline of California itself. What each point here is one district in the dataset. We are telling it to use a scatter plot. That's why we have all these dots here. This is the longitude, this is the latitude. Grid is true, and that's basically it. We basically get a map of California with one dot per housing district. Grid equals true just adds grid lines to help read the plot. And we do this to visualize the graphical distribution of the housing data. Now, just having dots here isn't very helpful. So we need to do this. We need to do more visualizations, at least visually, to kind of make ourselves comfortable with the data sets we have here. I assume the next image will be another one. So what do we have here? Again, it's the same kind of plot. We have the same kind of params here for longitude and latitude. And we have the alpha of 0.2. And why, in this exact case, why did we use alpha? It makes each point more transparent. Helps us see where points overlap, where there's a lot of them, like here and here and here, more inland. It helps us spot denser regions, and it avoids a clutter, so to say, because here we didn't know that these areas are so densely packed together, but only when we put the alpha here, we have somewhat a better idea of it. Let's do the next one. Okay, now this is a more complex scatter plot, so we do the same thing. Here I have the scatter. I'm using the longitude and latitude, and here are some other properties. This basically just creates a rich visual map where we have the usual kind of attributes. Here we have the size of the circle, which will be equal to the population. Okay, this is the label. I don't need this. This is the color. Goes from blue to red. And we basically learn a lot of things from this because we we know now that housing prices are very much related to the location. They are, if they are close to the ocean, if there is because these are here the most expensive ones, if there is a huge population density. Now the scatter plot also shows that expensive houses tend to be near the coast. High population areas also have high housing prices. And we also now, by looking at this visually, we know that there are some features that matter, like location, population density, and ocean proximity. They are really interesting. Housing plot, scatter, housing population. What if I print house? What will I get here? I would like to know more what these properties are doing more deeply. So the S or housing population actually sets the size. S is size of each dot based on population. Larger means more people. Dividing by 100 scales it down to keep the circles manageable. So if I remove this here, assume they will grow out of the proportion. Yeah. Okay. So if I divide it by, what if I divide it by 1000? Oh, they are really tiny. So 100 is optimal. I assume there is a certain value in which they are optimally sized. Label population. It's just a label used in the legend. I assume the C, I don't assume, I know that C means color. Basically, we use the median house value for color, and we map the color to the jet color map, which goes from blue, which is low, to red, which is high. And I mean, this is just useful for seeing value gradients. What else do we have? Color bar. Color bar just shows color scale on the side. This guy right here. What else do we have? Legend, ShareX. Okay, these are not. Let's go further. The argument ShareX equals false fixes a display bug. Okay, so this is hack in order to make this work. All right. I haven't seen this in the book, but the next snippet, the next cell generates the first figure in the chapter. This code is not in the book. It's just a beautified version of the previous figure with an image of California added in the background. Nicer label names and no grid. So it seems like it's the same thing. The only difference is I assume that we have the borders of the state of California overlaid here, and I'm just interested in seeing how it works. Download the California image. So we have California PNG. If we don't find it in the image path, file name. If it's not a file, we need to download it, I assume. So we go to here. We search for the file name, which is an interesting way and a smart way of writing this. Basically, we can just reuse california.png. We download it. We actually print that we are downloading it, and then we download it using URL library's request method. Using rename. Why are we Why did we rename this? Ah, okay. We are just making it cleaner here. And then we just plot this and but how where do we overlay the California image on this? Where is this even? Images, California, end-to-end project. Is it California PNG? How is it overlaid? I assume that it will, that the image on top of which it's gonna be overlaid will have the coordinates built in or automated, but here it seems that we need to, yeah. Basically he had to squeeze them properly. So if I put here, I don't know, instead of 1, 2, 4, if I put minus 12, I think this is gonna go. No. How is this working? I know that he's overlaying data on a real image to provide geographical context, but how is this axis thing working? It's a bounding box, I assume. So we have left. I assume this is right. This is top. I assume this is bottom. So it tries to write. I'm just interested in knowing how the author of this knew to use these exact coordinates. Wait, are these the real life geographic boundaries of California? So this is the westernmost latitude, longitude, easternmost longitude, southernmost and northernmost. This is just an image and nothing more. How does it line up with the data real world coordinates? That's the question I'm having. Is it possible that the only thing that he did was using the extent parameter? I mean, really interesting. I understand. I understand that this tells what is it? This is matplotlib. Yeah, I understand that this tells matplotlib. Okay, pretend this image california.png spans these longitudes and latitudes and coordinates, but the image it's it's still fucking pixels. You know how? What, it's 800 by 600 or some bullshit. How latitude and how does it know what latitude or longitude it represents by itself? Ah. Okay, let's talk correlations now. What do we see here? We see our housing data frame, and we see the core method. This method calculates the correlation matrix, which is a table that shows a relationship between numerical features. The correlation coefficient, or as it's known as well as Pearson's R, ranges from +1, which means it's perfectly positive. Maybe this is something worth scribing down. So what do we have? We have correlation matrix, which goes from -1, 0. Oh man, my hands are not very stable. +1 means that we have a perfect positive correlation. I don't know, for example, from our height and weight. 0 means that we don't have any correlation at all, and -1 means that we have a perfect negative correlation. For example, smoking and lifespan. And we can also create an example in which we create a new data frame. Imagine that I created it using pandas, but for now I'm only gonna have income will be an array. And let's say value. We are still talking about houses. 100, let's see, 50, 200, 250, and let's see, 300. And if we run the correlation matrix, what will happen is that we will have an income here, an income there, because of course it's a matrix. And then we have value. Then we have value, which basically means, okay, income and income are not important, but value and income, if you take a look at them here, value and income have perfect correlation, basically meaning as income increases, the value increases as well. So I think that's it when it comes to the theoreticals. I'm gonna close this. And here I have the correlation matrix that I created, and now I'm pulling from it the median house value, and I'm sorting it by other attributes that are correlating to this attribute in a descending value. Just a second. Alright, let's maybe just see. So the median house value is highly correlated to the median income, to the amount, okay, maybe not the amount. So all of these are dangling around the middle. It's somewhat negatively correlated to latitude, but I don't know how important and valuable this data is. Let me see if I have any other data. And let's now open it in text editor completely, yeah. Okay, longitude and latitude, I don't think they are. Maybe the median age can be interesting. Maybe total rooms can be interesting as well. Let's print some of these. Housing median age. What else do we? Total rooms. I would assume a house with more rooms is more expensive. Income maybe. Median income. And let's maybe even population. Let's see if there's any correlation between population and the price of housing. Population. If I run this, it only prints out the latest guy, so I need to print each and every one of these assholes. Up, 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 up. Up, 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 up. Let's open the whole. This editor could not open due to unexpected. Why do we have unexpected errors? We have unexpected. Why can't you open this guy? It has no errors. It has no errors while building it. Why do I have errors? No idea. I don't care. I just wanted to see if there are any settings for it. I don't care. So the house value has these correlations. The median age doesn't have. It's somewhat correlated to the house value. But it's negatively correlating to the amount of total rooms and the amount of population. Interesting. What else do we have? Total rooms. No, they are not. They are not. Income. Okay, income is related to the value. Population is related to household. Yeah, this makes sense. More household, a bigger population, more population, more bedrooms, more population, more rooms. All right. Interesting. We pulled out some pretty interesting conclusions here. Okay, let us hit the next cell. Okay, let's talk now scatter matrix. So what does it do and why do we use it? Basically, as you can see on the video here, the scatter matrix creates a grid of scatter plots, and every attribute on the list is plotted against every other attribute. And the diagonal often shows histograms of individual variables in order to understand the distribution. For example, here we have the median income, which is this one. It's not a scatter plot. This is just a histogram of the income, the household. Basically, we run this in order to give a visual correlation map for our features. So in our specific case, how many do we have? We have 4 attributes. So we would get 4 by 4. 4 times 4 is 16. We would get 16 plots. One for each of the combination. Median income versus total rooms. I assume this is total rooms, yes, which is this guy right here. Median income versus housing median age, which is this guy right here, and so on and so on. Basically, we do this just to spot relationships between variables, especially linear, nonlinear, or clustered pattern. And with this, we can actually exploit and expose strong linear relationships, like in this case, in which we compare our median house value against the income of the household. Why did we focus on only 4 features? Because the full dataset has 11 numerical attributes, which means if we would multiply by each other, we would get 121 plots in a full matrix. That's too dense, too expensive on the computation, too hard to read. So we focus on attributes that we think. Again, here is the data scientist factor at play here. We focus on attributes that we think correlate most with our target. So we have run this, and now we have visually. Now we can visually experience the correlations as well. So basically, how do we know that? How do we know that some attributes are potentially strong predictors? What makes a feature promising? The only thing that makes a feature promising, it's a high correlation matrix. Everything was total rooms, but this in yeah, let's talk median house value. This property right here. This is a strong positive correlation with median house value. basically as we approach 1 or -1, we indicate a strong linear relationship. Also, if we can plot our data, we can also see a clear upward trend. For example, here, in which all the points are going up in this way, or even here, which they are going more to the right. It's not noisy. I mean, it is noisy. It looks noisy, but it shows a strong structure. It shows trend. This one is just noisy. This one doesn't do anything, but this one shows a trend. I think we can even run another guy here. Let me just try to I even have from import Seaborn SS. Okay, we have SNS. No, what have I clicked? I have clicked something and I messed with some. Okay. Module not found there. Okay, so we don't have Seaborn. I have Seaborn. Why don't I have Seaborn? Oh, I need to install it. Like, looks cool, looks interesting. Okay, maybe let's skip it for now. Yeah, this is basically the same figure here, only extracted. And we can see the trend of the. We can also see all the values that were capped here at 500k as well. So we need to do something with these values in the future, but for now, it's good that we have found a way to visualize our data. So what is this doing? Experimenting with attributes combination. So we created a new property. We created a couple of new properties. The amount of total rooms divided by the amount of household. Yeah, this makes sense. This makes sense. Does it make sense? Print housing rooms. How these properties look like? Ah, so it's total rooms based on district. So it's total rooms in every household. Once we divide the amount of total rooms by household, we will have rooms per house. Bedroom ratio, okay. People per house, okay. This is also quite a interesting property. So the house bedrooms ratio have a negative correlation with the median house value. I'm interested in how bedrooms ratio have a negative correlation with this. Okay, we are just creating new properties, new features from existing ones. Average number of rooms per household. Proportions of rooms that are bedrooms, average number of people per household. What bedroom ratio actually represents? It represents the amount of housing density and simplicity. A high ratio means that most rooms in the house are bedrooms. Fewer rooms are used for living, dining, offices, and other things. Which means that these houses are likely smaller, they are more crowded, more utilitarian. A certain amount of people could be living it, like foreign workers and stuff. But a lower ratio implies that there's a lot of living rooms, multiple bathrooms, kitchens, maybe offices. Suggests that they are larger, more luxurious homes. So as bedroom ratio decreases, median house value tend to decrease, which is useful, extremely useful. Okay, prepare the data for machine learning. Let's do this the next time.